When we put one quantum of energy into the principal quantum number and let L equal to 1, it gets a little more interesting. Now we've got three states, m sub z equal minus 1, 0, or 1. So now I've got my z-axis here, and I better give myself about 2 total units in absolute value there. Those are going to be my h bars. So the L squared, the total angular momentum squared, is equal to twice h bar squared. L times L plus 1 is 2. That means the total angular momentum is equal to h bar times the square root of 2, or 1.4 h bar. The z component of the angular momentum can be minus 1 h bar, 0, or plus 1 h bar. So let's place this here. We've got a total angular momentum of 1.4 h bar. And so the vector corresponding to that total angular momentum is going to be somewhere on a sphere, which we're just drawing a section here in the sort of z-axis, any plane that goes through the z-axis here, of a radius 1.4 h bars. But now the thing is that if the z component of the angular momentum could be anything, then this vector of total angular momentum could be just oriented anyway. I could draw any vector I wanted, but the z component of the angular momentum can't be anything. It can only be negative 1, 0, or 1. And so, given that, there's only these three possible values here. One orientation is any vector that sticks up exactly 1 unit of h bar into the positive z direction. So this red arrow here shows an angular momentum vector of total length, amplitude 1.4 h bar, but the z component is 1. I have no idea which way that is pointed in x and y. It's completely undetermined, the xy orientation of that. But I know that the z amount of it is specified at 1 unit. I can draw another one at 0 units. Same thing works. And then finally I can draw one at negative 1 unit. So these three vectors are the only possible z values. In each case, again, the x and y components of this are not constrained at all. You can actually very literally think of it like a precessing top. The z amount stays constant, but you could almost think of that red vector as spinning around in the xy plane, but it's not really spinning. It's just not determined. We don't know which way that points at all. So these three different z components are the only three situations where we both have a total of 1.4 h bar units of angular momentum, and also the right three z components of the angular momentum. For this reason, we tend to call the m sub z bits the quantization of orientation, because what they're basically doing is controlling which directions this spinning dumbbell is allowed to spin in. So now if we look at what the wave function looks like, we're going to start with a plus or minus 1 m sub z, because they look basically the same in either case. The function here is root 3 over 8 pi, and there's a sine theta, and then 1 unit of slinky, so there's an e to the plus or minus I phi. So what this is going to look like is the sine theta part just looks like this blue curve here. I've just drawn it out into the x-axis here. But when theta is equal to 0, which means we're sort of pointing in the plus z direction, the function is 0. And then as we head down to theta equals pi over 2, then it's 1. So when we get down to the x-axis, it's at its maximum amplitude. And then we work our way back around to theta of pi, which is pointing down in the z direction. That's the largest value of theta that we're allowed. We roll back around. So we just have this circle, in fact. And that can go in any direction. So there's a negative x direction. Here's a negative y direction. Finally, a positive y direction. So the theta part of it is just this sort of circle there. It has no node. We'll get to that in a second because it never quite crosses 0. It touches 0, but it never crosses 0 due to theta. Theta doesn't make it cross 0. However, as we go around the circle in phi, we go from +1 when we're in the x-axis, and then we go to the plus y direction depending on whether our m sub z is positive or negative. We get to plus or minus I. Then we get down to -1 around there, 180 degrees, pi around the circle. And then we get to minus or plus I when we come to 3/4 of the way around the circle, pi over 3 pi over 2. And then finally we get to 2 pi and we've come full circle again. So the sign is changing, but it's changing through this complex cycle instead of going through a 0. So it's got one unit of slinkiness, basically, and that's because of that e to the plus or minus I phi part there. So there's no nodes in theta. It never quite crosses 0 as we vary the theta coordinate, but it does have one cycle in phi, and so in total there's going to be one total angular node in the system. Now let's look at the other one. So in the other case, we have the y 1, 0. So in this one, the numerical function is the square root of 3 over 4 pi, slightly different, and then we have a cosine theta. And that's it. Because m sub z is equal to 0 now, e to the I 0 phi is just 1, and that disappears. So there's only a cosine theta dependence. And now as we go from theta equals 0 to theta equals pi, from the plus z to the minus z direction, first we start out at 1 and we head our way down toward pi over 2, and we go from 1 down to 0. And then as we go from pi over 2 to pi, the cosine goes through its negative phase. So we go to a negative number there as we go from pi over 2 down to pi, pointing in the negative z direction. So I'm just going to use two different colors to indicate whether the function is positive or negative when we're pointing in that particular direction. But then as phi varies, the function doesn't change at all. There's no phi dependence, and so we can close these circles and in fact wrap them around, because the function doesn't change at all as I spin around in the phi direction. So there's just a positive lobe there and a negative lobe there, kind of clustered around the z-axis. This ought to remind you a whole heck of a lot of a pz orbital. But the important thing to realize is the z component of the angular momentum is 0 because the thing is spinning around. The angular momentum vector is in the xy plane, which means the probability of finding the mass or the diatomic masses out of the xy plane is extremely high, because the way that you get the rotor of the propeller to be in the xy plane is to have the darn propeller spinning outside of the xy plane. So now we've got one theta node. We really do cross 0 in theta, but there's no dependence on phi at all, so there's no cycles in phi. And once again, we have one total node in this solution. All right, we're going to look at just one case for L equals 2. So the full set of functions for L equals 2, we have y2, and then m sub z can be -2, -1, 0, +1, or +2. So all of those are possibilities, which means that now, if we look at our little circle of vectors here, we better go to about -3 and about +3, because the total angular momentum is the square root of 6 h bar, which is about 2.5 h bars, which corresponds to a circle that looks something like this here. And now the m sub z component can be anywhere from -2 to +2. So you see, always, 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 the total angular momentum, it winds up essentially describing a circle that's ever so slightly bigger than the m sub z components, which means the m sub z is never able to grab all of that total angular momentum. There's always a little slop. There's always a little bit left over, and that's one of those quantum uncertainty things that always comes into play. But basically we can have +2 h bar, +h bar, 0, -h bar, and -2 h bar. So now there are 5 possible orientations for that total angular momentum vector that has the right length, about 2.5 h-bar, and also has the right 5 different potential orientations of the z component of the angular momentum. Once again, the xy orientation of those vectors is totally undetermined. We've got no idea which way that's pointing, which is why I haven't even drawn any xy axes there. If we pick one out to look at, the most interesting one would be y21. So we're going to give it 1 unit each of, well, we're going to give it 2 units of total angular momentum, but just 1 unit of z angular momentum. So the function here is root 15 over 8 pi, and there's a sine theta, cosine theta now, and a 1 unit of slinky, so an e to the I phi. So the sine theta, cosine theta thing is a little more interesting, as it starts out when theta is 0, then the sine theta part of it sends the function to 0. And as we go into positive theta, away from that, cosine theta is large and sine theta is growing, and so at first the function starts to grow, but then cosine starts to drop off, and so by the time we get down to theta of pi over 2, the function drops back down to 0. And then we go down in the negative direction. I'm drawing this thing in the y plane, in the yz plane at the moment, by the way. So then we go from 0 to, we go from pi over 2 to pi, and we repeat this little sort of flower petal, but with a negative sign, because now the cosine is negative. So that's what the theta dependence does, going from 0 to pi. But phi is also doing a thing here. So this slinky dependence, as I go around the circle in the xy plane, is going to be doing something. So we're going to have these lobes here as we go around in phi, the positive value there and the negative value there. But what's actually going on as we go around in phi, the reason we go from that top purple positive to blue negative is that as we spin around that xy plane, we basically go from, as I've drawn it in the y-axis, I to -1 to minus I, back to +1 in the positive x direction. So we flip the sign by spinning halfway around the circle in using phi to do our little spinning. And so that's how it gets the other part of that. That's how you basically change sign on those lobes there. The theta dependence itself only changes sign as we go from above the xy plane to going down below the xy plane. And it's phi that's taking on the job of changing the sign as we spin around the z-axis. So it's got some of each. We've got one theta node, because we do change sign as we go through the xy plane. But then we have one cycle in phi because of that dance from 1 to I to -1 to minus I as we go around in the phi direction. And there's a total of 2 nodes. And indeed, all of the functions have 2 nodes with L equal 2. A really important thing is any amount of z angular momentum is going to make there be some sort of node at the z-axis. So there's going to be, it's not a theta node, but there's going to be a dimple. The function is going to have to go to 0 at the z-axis, and then because we spin around in phi and go through a phi cycle, we're going to get the change of sign in phi there. It's not a theta node, but if there's z angular momentum, if there's any amount, that means there's some rotation in the xy plane. There's some amount of rotation in there. There's no way that you can find the object right on the z-axis, because then the radius out from the z-axis would be 0, and it's impossible to have a moment of inertia. So if there's z-component angular momentum, the function must go down to 0 as you get to that z-axis. That's a requirement. And one of the reasons I'm stressing this is I am going to want you to be able to basically sketch what these functions ought to look like. I am going to want you to be able to think through what the quantum numbers must be if you see a certain kind of function. And so we're emphasizing the number of theta nodes, the number of phi cycles, the total angular nodes equaling the L quantum number, the principal quantum number, and the total number of cycles being given by the absolute value of the m sub z quantum number. Again, because we didn't cross 0 there at that cusp, it's not a theta, because theta only goes from 0 to pi, as we've drawn it here in this gray. So that's basically the bottom line there. I want you to be able to identify what are theta nodes, what are phi cycles, and to be able to suss your way through what these rotational wave functions look like. The good news is they're orbitals. You're used to looking at these guys. You're used to thinking them through. And now we're just giving you the sort of theoretical chops so that you can actually understand and talk about where they came from.